Okay, well my name's Hugh and I want to show you this system that we've put together for measuring the lowest levels of sulfur gases like hydrogen sulfide, carbonyl sulfide, dimethyl sulfide, ethyl and methyl mercaptan, those kind of sulfur gases. So this system is designed to measure the lowest possible amount. We can't get much below 1 part per million by the traditional arrangement. The traditional arrangement has a flame photometric detector and a column. In this case, we're using an RTX Q-plot column to separate especially the CO2 away from the hydrogen sulfide. And then in the column oven, there's a Valka valve, which traditionally is used to inject the contents of a 1 milliliter loop. But in this case, we've substituted this arrangement over here for the loop. And what this is a cryogenic trapping system. It relies on a relatively new development, which is a low-cost, relatively low-cost, portable cryogenic refrigerator. So this refrigerator is about 40 pounds. It's relatively constructed. It's designed to transport organs around from hospital to hospital. So they get it really cold, they put the heart or whatever it is in there, and then they drive it around or they take it on a helicopter to the hospital. So it's intended to be a portable cryogenic refrigerator, and it costs about $6,000. So inside this refrigerator we've put the substitute for the loop, which we call a trap. So here the refrigerator's on, and let's get a shot of the control panel of the refrigerator over here, and you can see that right now the refrigerator is saying that it's at minus 58 degrees centigrade. If I push this button, it tells me what the set point is. It says S, and then it says minus 60. So the refrigerator is just a couple of degrees warmer than what it's supposed to be at, but it'll cool back down. It gets warmer because the thing inside the refrigerator, the trap, heats up, and so the refrigerator then has to remove the heat that the trap generates as it heats up. So here's the lid, and then there's this inner lid. You can see there's some frost accumulating on the inner lid. That's probably because there's a tiny little leak in this gasket. The gasket is supposed to keep the ambient air from leaking in, and of course ambient air has a huge amount of water, so it makes this frost. So let's see if we can get a shot inside that. So what we have down here is we've got a little fan that moves the air around. Now that's something that I put in there. I attached that fan to the inside of here, and that's just to make sure that the air circulates inside this very, very cold chamber. And then we have the trap. So the trap looks like this. It's a Teflon tube inside of an aluminum jacket, and there's 2 heater cartridges. So when the software says to heat, then this part of the tube gets hot, and inside this tube there's something called silica gel. So the tube is a Teflon tube, just a 1/4-inch Teflon tube, and it's filled with this powder called silica gel, which is relatively efficient at trapping hydrogen sulfide, but not efficient enough to do it at room temperature very well, at least not to get down to these low levels. So the idea is that we put the trap inside of this cryogenic refrigerator, and it's minus 60 degrees, so that causes the hydrogen sulfide to really stick to the inside of the trap. So one of the issues with the trap, though, is water, because we're sampling from the ambient air. There's a lot of water that also goes into this, so keeping the trap from getting plugged up with ice is a big issue. So that's why this is so long. So the silica gel is really just 2 inches worth of silica gel right in the middle of this heater. So the rest of this tube is blank, and I don't know if you can see it from the video, but you can see that there's a lot of ice, or slushy ice, it looks like right now. It's melting because I've got this open, but the ice is accumulating here. So that's one reason why we made this so long, is that periodically what you have to do, you don't want to open this, because when you open it, it warms up and it takes a long time to cool back down. So if I shove this through the wall, say, watch, I'll do it from this angle over here, where I grab it from the outside, and then I can pull this right up to the wall, and hopefully what I can do there is, from this side, all the ice that has accumulated on the inside of the trap, we can melt that ice without having to open the refrigerator, because that causes a delay while it cools back down. So if you can just shove the trap in like this, the idea is that the ice is going to accumulate early in this little piece of tubing because it's cold, and then periodically you pull it out and then encourage the ice to melt by just warming it with your hand if necessary, or I suppose you could use a heat gun, but just warming it with your hand usually causes the ice to melt. And then you can just pull this out like this, and the water hopefully will just drip out. So we've tried to minimize the buildup of ice by using a dryer. This thing here is a sample stream dryer, and what it is it's a Nafion tube inside of this plastic container. I don't know if you can see the Nafion tube inside there, but it's buried in this desiccant, which keeps the outside of the tube very dry, and the gas that passes through the inside of the tube, which would be the sample, gets dried out by contact with the wall of the Nafion, which sucks the water out from the wet side to the dry side, but hopefully does not also extract the hydrogen sulfide. In other words, the hydrogen sulfide goes through the tube and then into the trap where it gets stuck, and the water stays in this desiccant. That's the hope. Okay, so this is how the system is intended to work. So I could either take my sample in the form of a small syringe or in the form of a Tedlar bag. So if we do the Tedlar bag approach, which is not the best because small amounts of sulfur tend to get stuck on the inside of the bag and just never come out. You put them in, but they don't come out. So the system really is intended to monitor the sulfur content in ambient air. For that, you really wouldn't connect anything to this hole here. You would just let it suck ambient air on through. But if you're connecting a bag, then you take and you fill the bag up. One way to do that is with a little air compressor. I have one here. So I'm going to blow the bag up with room air. Now, this is a 2-liter bag, and that is roughly what the system will suck through in a 5 to 10 minute period. So the flow through the trap depends to a certain extent on how ice saturated it is. If it's clogged with ice, then it flows a little slower than if it's free and clear. So, but roughly the suction through the trap is about 100 milliliters per minute. So that would mean it would take about 20 minutes to completely empty this 2-liter bag. But the 2-liter size is a good size to work with. So we pump up the bag, and then I have this little thing that lets me interface that to the inlet of the system. So this is where the sample goes. So if it was just room air that we were monitoring in the bag, we would just start the analysis right now. But I'm going to put a little bit of sulfur in the bag. So here's a standard of hydrogen sulfide, and this is 100 ppm of hydrogen sulfide. So I'm filling my syringe, and I'm going to take 2 milliliters of the 100 ppm hydrogen sulfide. And that's what this standard is. It's actually 94.9 ppm, but we'll just call it 100. And then I'm going to push the 2 milliliters of 100 ppm hydrogen sulfide into the bag through this little rubber septum. So there it goes, and I'm going to squirt it in there. Okay, so now I've diluted the 100 ppm hydrogen sulfide by 1,000 times by putting it into a 2-liter bag. That's 2 milliliters into 2 liters. That's a dilution of 1,000. So presumably now there's 100 parts per billion of hydrogen sulfide in this bag. So we start the analysis by hitting the space bar or pushing the start button on the GC. And the first thing that happens is the vacuum pump turns on. You could hear that. There's a little buzzing in the background. And this component here, the vacuum pump, is connected to the GC. So the GC can turn the vacuum pump on and off. And when it does, the vacuum pump, which is connected right here to the outlet of the gas sampling valve, is sucking the sample through that cold trap that's in there. So hopefully all the hydrogen sulfide gets stuck on the trap, and then subsequently in the analysis the trap will heat up. It'll heat up to around 180 degrees, and then the valve rotates, and the hydrogen sulfide molecules that were stuck on the trap now depart and into the GC. So one thing that's important is to know roughly how many milliliters per minute is going through that trap. So one way to know that is to take a syringe like this. See, I'm going to pull the plunger back to 50 milliliters, and then I'll disconnect this just temporarily and connect this syringe, and you can see the plunger moving. So you would really just time how long it took the plunger to move 10 milliliters. So I'm going to start counting when it gets to the 40. So that's 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009. So roughly 9 seconds to go. 10 milliliters, so that would mean about 70 milliliters per minute was flowing through that trap. So once the trap gets hot, once it dumps all the molecules onto the column, and then we get a chromatogram. So here's a printout of a typical chromatogram when doing this. So there's two peaks that come out that are pretty close to each other, and they're significant because this first one is carbon dioxide and the second one is the hydrogen sulfide. This third little one is carbonyl sulfide, and then this one later on is dimethyl sulfide. So these are the three sulfur molecules that I'm kind of working with. You could have others, but right now just that's what I have as a standard. So one of the problems that we had initially with this is that if the carbon dioxide comes out at the same time as the hydrogen sulfide, then you don't see the hydrogen sulfide at all because the carbon dioxide prevents the detector from seeing it. So there has to be separation between the carbon dioxide and the hydrogen sulfide. So the way to do that is to use a column that does that. So that's why we're using this particular column that we have in the column oven. It's a plot column. It's called a Q plot, and it does a nice job of separating carbon dioxide from hydrogen sulfide. It's not so good at separating the higher boilers, but it's a compromise. So but it is very necessary to separate the carbon dioxide from the hydrogen sulfide, and there's a lot of carbon dioxide in air. There's 400 parts per million of carbon dioxide in air. So carbon dioxide has a very similar boiling point to hydrogen sulfide, about -60. So carbon dioxide traps also very readily on this trap. So when we're trapping hydrogen sulfide, we're also unavoidably trapping the carbon dioxide, which is there at 1,000 times greater concentration. So there's a lot of it trapped, and we have to make sure it's chromatographically separated from the hydrogen sulfide. Otherwise, you just don't see a hydrogen sulfide peak. Okay, so that's really the story on this cryogenic trapping system. The unfortunate thing about the flame photometric detector is that it has a quadratic response. So that means when you're measuring something that's 10 times lower, the peak is 100 times smaller, not 10 times smaller as you would expect, but it's the square response. So if you inject 10 times less, you get a 100 times smaller peak. So what that means is that if we can increase the amount of sample that we're able to inject onto the GC, so turning parts per billion into parts per million, we have a hope of detecting the low levels of sulfur molecules. So thank you. That's the story on this particular system.